We shall now impose certain conditions on the topology to obtain some particular types of topological space. This condition called separation axiom are as follows. First definition, that is T2 space due to Kolmogorov. That means Kolmogorov first introduced the definition of T0 space. What is that? Every pair of distinct point in X tau, there exists a neighborhood of one of those points which does not contain the other. And second definition, T1 space due to Fachet. For every distinct point x and y in X tau, there exists a neighborhood u and v such that x belongs to u, y belongs to capital V, but y does not belong to u and x does not belong to v. Third important definition is T2 space or Hausdorff space due to Hausdorff. That means Hausdorff first introduced the definition of T2 space. The definition is every pair of distinct points x and y in capital X, there exists two disjoint neighborhood u and v such that x belongs to u and y belongs to v. Thirdly, we define T3 space due to Victorius. Any closed set f and any point x in f are always strongly separated in X tau. Strongly separated means there exists two disjoint neighborhood u and v such that x belongs to u and f subset of v. Next, we introduce the definition of T4 space due to Tz. Any two distinct closed sets f and g are strongly separated in X tau, that is, there exists two disjoint neighborhood u and v similar as f belongs to f subset of capital U and g subset of capital V. Next, we introduce the definition of regular space. If X tau is a T3 space and also T1 space, and the definition of normal space if X tau is a T4 space and T1 also, then it is very easy to prove that a normal space is always a regular space and a regular space is always a T2 space and a T2 space always a T1 space and finally a T1 space always a T0 space. But the converse of the result is not satisfies. For example of a T0 space which is not a T1 space, let R tau be a topology whose member are phi, R and all those sets of the form open A to infinity, where A belongs to real number. Note that in this space for x, y belongs to R with x strictly less than y, there exists an open set containing y but not x. For example, we consider the interval open x and open infinity. So tau is a T0 space although there exist no open sets which contain x but not y. This implies tau is not a T1 space. Next, we consider another example of a T1 space which is not a T2 space. We consider a topology tau is, that is nothing but it is a, we consider the topology a cofinite topology on R and xy belongs to real number with x not equal to y. Let us consider two open sets as u is equal to r minus singleton y and v is equal to r minus singleton x. Then obviously x belongs to u and y belongs to v, but u intersection v obviously not equal to phi. So it is a T1 space although there exists no open sets u and v such that x belongs to u and y belongs to v, for which u intersection v is equal to phi. This implies tau is not a T1 space, not a T2 space. Next example of a normal space, regular space and T2 space. is the usual topology on R. Proof is very simple, so omitted. Next we introduce another theorem. A topological space X tau is a T1 space if and only if every one point set is a closed in X tau. Let X tau be a T1 space and consider a singleton set and X, it is a one pointing set of X, and choose Y, any other point in X other than X. Then by the axiom T1 there exists an open set V such that Y belongs to capital V and X does not belong to V. Hence Y cannot be a limit point of the set X. Consequently, singleton X is a closed set. Thus every one pointing set is a closed set in X tau. Conversely, let X tau be a topological space in which every one pointing set is closed. Then singleton X and singleton Y both are closed. That means X minus capital X minus singleton small x and capital X minus singleton Y both are open sets, and hence capital X minus small x is a open set containing Y without containing X. Similarly, capital X minus singleton Y is a open set containing X without containing Y. Thus X tau is a T1 space. Next example, so that let X tau is a indiscrete topology and Y tau dash is a T0 space. If f is a mapping from X to Y is a continuous, then f must be constant function. Proof is, if possible, let f is not a constant function. That means there exists two points x1, x2 belongs to capital X such that f of x1 is equal to a and f of x2 is equal to b, where a not equal to b, as X tau is a T0 space. As Y tau Y is a T1 T0 space, there exists a open set V belongs to tau dash such that V contains one only of the point A and B. So V contains A but not B. Since x1 belongs to F inverse V and F inverse B is a proper subset of X and F is a continuous function, so F inverse V obviously belongs to tau. Hence F inverse V must be equal to phi. Since B does not belongs to V, that implies x2 does not belongs to F inverse V, and the topology tau is indiscrete topology. But then x1 belongs to F inverse V and this is equal to phi, which is impossible, so F must be a constant function. Next theorem introduce the following conditions are equivalent for a topological space X tau. Condition 1, that means X tau is a T1 space, and next it is equivalent to every one pointing set is closed in X tau and every finite set is a closed in X tau, and every point X belongs to capital X, and the set of all limit point of this one pointing set is equal to phi, and for every subset A subset of X, the intersection of all open set containing A is the set A. Next we introduce the definition of a convergent sequence. Let X tau be a topological space. A sequence xn in capital X is said to be a convergent to X belongs to capital X if for every open set U containing X there exists a natural number k such that xn belongs to U for all n greater than or equal to k. The point X is called the limit of the sequence xn. Next theorem, any convergent sequence in a Hausdorff space possesses a unique limit. Proof is, if possible, let the sequence have two distinct limits, say x and y. Since X tau is a T2 space, so there exist two neighborhoods U and V such that X belongs to U and Y belongs to V, and U intersection V is equal to phi. Again, by the definition of convergent sequence, we get xn belongs to U for all n greater than or equal to some positive integer k1, because U is a neighborhood of X and xn is converse to X. Similarly, xn is also converse to Y, so and V is a neighborhood of Y, so xn belongs to V for all n greater than or equal to k, where k is another integer. So xn belongs to u intersection v for all n greater than or equal to maximum of k1 k2, and we know that u1 intersection v is equal to 5 because it is a T2 space or Hausdorff space, so which is impossible. This proves the theorem. Next we get the regularity criteria. A topological space x tau is regular if and only if every point x belongs to capital X and every neighborhood u of x, there exists a neighborhood v of x such that v bar subset of u. Introduce normality criteria of a topological space. A topological space x tau is normal if and only if every closed set f and every neighborhood u containing f, there exists a neighborhood v such that f is a subset of v and that v subset of v bar, that is v union is limit point and this is equal to subset of u. Next we introduce very important a lemma, and that is known as well-known lemma, that is known as Urason lemma. In a normal space x tau, if a and b are disjoint closed sets in X, there exists a continuous mapping fx to closed interval 0 1 such that fx equal to 0 if x belongs to a and it is equal to 1 if x belongs to b. Finally, we introduce another important theorem, that is Teach extension theorem. Let x tau be a normal space and f be a closed subspace of x, and let f small f is a mapping from capital F to closed interval AB be a continuous function, then f has an extension h over x with the value in AB. And that's all. Thank you everybody.